Hello, sorry I couldn't be here for you today, so hopefully this video lecture will suffice. I think what we should do to start off with is just go over one of these combustion analysis problems. This really ties together lots of the things that we've been doing in the last couple of weeks, and this will likely be a bonus question on the test. So if you're doing really well and you want to challenge yourself, this is a perfect thing to work on. If not, maybe you can watch this, but work on the other stuff, just like calculating moles, naming compounds, things like that instead, because those will be far more important on the test. But this is important to learn nonetheless, just because it ties together lots of the things that we've gone over so far. So the question reads, 29.9 grams of an unknown compound containing only carbon, hydrogen, and oxygen is burned to produce 41.1 grams of carbon dioxide and 11.2 grams of water. So what we want to do, or what the question is asking us to do, is to identify the empirical formula. And if you've seen this question before, I think it's question 3.64 to 3.68 on Top Hat. So to start off with, let's just consider what's happening here. Our unknown compound, which I'll title X, is burned in oxygen to produce water and carbon dioxide. So in this reaction, we know where the hydrogens come from. The only source of hydrogen is the unknown compound. We know where carbons come from. The only source of carbon is the unknown compound. And oxygen came from both, potentially. It could have come from this oxygen as well as from the unknown compound. So we're going to find out how much hydrogen and how much carbon we have in a slightly different way than we'll figure out our oxygen. So to begin, let's convert carbon dioxide to moles. So we have 41.1 grams of carbon dioxide. And in order to convert it to moles, we're just going to multiply by 1 mole over the molecular weight. So multiplied by 1 mole CO2 for every 44.01 grams CO2. And again, this 44.01 grams just came from the periodic table. I just looked up the mass of carbon and added it to 2 times the mass of oxygen. So at this point in the question, grams carbon dioxide cancels with grams carbon dioxide, and we're left with moles of carbon dioxide. But we really want to find out how much of that is carbon and how much carbon came from the initial unknown compound. So what we can do is we can just use the ratio of carbon to carbon dioxide to figure out how much of this is just carbon. So multiplied by 1 mole of carbon for every 1 mole of CO2. And the reason I know the ratio is 1 to 1 is because just looking at carbon dioxide, I can see there's only 1 carbon for every 1 carbon dioxide molecule. So 1 to 1 ratio. So let's solve here at this point. And what I'm going to do is I'm always going to keep 2 additional significant figures from what I should have. Looking at the question, we need 3 significant figures, so I'm always going to use 5 until the very end, and then that way we won't encounter any rounding errors. So 41.1 times 1 divided by 44.01 equals 0.93388. And then multiplied by 1 over 1 equals 0.93388. And this is, again, moles of carbon dioxide canceled. So we figured out how many moles of carbon. That's going to be useful at the end of the question, but what we're going to need to find oxygen is how many grams of carbon. So let's convert this to grams as well, multiplied by, and to convert it to grams, just multiply the number of moles by the molecular weight per mole. So 12.01 grams carbon for every 1 mole of carbon equals, and I got 11.216. And that's grams carbon. So we're going to need this number here to figure out our oxygen, and later on we're going to need this number here to figure out our empirical formula. So we've done this for carbon. Let's do the exact same thing again for water. So at this point, if you'd like to try doing water, if you didn't get this when we went over it in class, just pause the video and try and follow this exact same format for water, and I'll do it right now. So we have 11.2 grams of water, and multiply that by 1 mole water for every 18.02 grams water. And in doing this, we're going to find out how many moles of water 11.2 grams is. Grams H2O cancels with grams H2O. And now let's multiply it by the ratio of hydrogen to water to figure out how much hydrogen is in that water, or how many moles of hydrogen. So this time it's not a 1-to-1 ratio. I can see that there's 2 hydrogens for every 1 H2O molecule. So I'm going to write 2 moles hydrogen for every 1 mole H2O. And let's solve and find the number of moles, which we're going to need later for the empirical formula. 11.2 divided by 18.02 equals 0.62153, but this time multiplied by 2 over 1. So equals 1.2431, and this is moles hydrogen. And again, I'm going to keep this number in mind for figuring out the empirical formula, but to figure out oxygen, I need the grams of each. So let's multiply it by the molecular weight of hydrogen, and just 1 hydrogen. We already accounted for the fact that there's 2 hydrogens here, so just 1.01 grams hydrogen for every 1 mole hydrogen, and that 1.01 just came from the periodic table as well, the molecular weight or the atomic weight of hydrogen. So multiply by 1.01, and I end up with 1.2555, and this is grams of hydrogen. So I calculated both of these values in grams, and the reason I did that is because in the question, I'm given the number of grams of unknown compound. So I know that the unknown compound is made out of only carbon, hydrogen, and oxygen, and now I know what mass of carbon and hydrogen I have. So the remainder of the mass is just going to be made up of oxygen. So what I can do is I can take 29.9, and then I can subtract the value of carbon from it, and subtract the value of hydrogen from it, and then I'll be left with how much oxygen is there. So I'm going to do that maybe right over here. 29.9 grams minus 11.216 grams plus 1.2555 grams and I got, oh, I typed that in my calculator wrong. $17.429. And this is oxygen. So just looking back and keeping track of my significant digits or significant figures here, this answer has 3 significant figures. This answer has 3 significant figures. When we're looking, 3 significant figures, 3 significant figures. When we're looking at subtraction or addition, we care only of the decimal places. So this answer has 3 significant figures as well. This isn't going to be super important for this one because we're figuring out the whole number ratio of one atom to another. So there's only really going to be 1 significant figure in our answer because it's the quantity of something. There's either 1 of the thing, there's 2 of the thing, there's never going to be 2.85 of the thing, or any fraction of the thing. So we know exactly how many grams of oxygen there are, But now to figure out the ratio of oxygen to hydrogen to carbon, we should convert that to moles. So we already have moles of hydrogen, we already have moles of carbon. Let's figure out how many moles of oxygen there are. If you want to pause this and take a second to do this or on your own, that's fantastic. If not, follow along with me here. We know the number of grams, so all I have to do is multiply it by 1 mole of oxygen for every 16.00 grams of oxygen. And this equals 1.0893. And this is now moles oxygen, so grams oxygen cancel with grams oxygen. And I'm just going to put a box around this one too so we can identify all of the numbers of moles. And now I know the number of moles of carbon, the number of moles of hydrogen, and the number of moles of oxygen. The next thing to do here is divide each one of these values, 0.93388, 1.2431, and 1.0893, by the lowest of these three values. So considering these three numbers, 1 point something, 1 point something, 0.93388 is the smallest number. So to figure out carbon, 0.93388 divided by 0.93388. To figure out hydrogen, 1.2431. And divided by, you guessed it, 0.93388. And to figure out oxygen, 1.0893. Divided by, hopefully you've got it by now, 0.93388. So each one of these numbers of moles is divided by the smallest number of moles. And the reason we're doing this is because we want to get a whole number ratio, and a great place to start is by having one of something, and then we'll figure out how to get a whole number ratio from that. So one of something, 0.93388 divided by 0.93388 is 1. So there's 1 carbon, and then 1.2431 divided by 0.93388. I have 1.3311, and this is moles of hydrogen. We can see that's not a whole number, but we'll fix that soon. And then for oxygen, 1.0893 divided by 0.93388, and I got 1.1664. And that's moles of oxygen. So this part is possibly the most difficult part to figure out here. What I want to do is I want to multiply all three of these numbers so that they work out to be about whole numbers. And I have to multiply them all by the same thing. So something like 0.33, I could see if I multiplied by 3 would come out to a whole number. So 1.33 times 3 equals 3.99. That would be great for this one. It would be great for this one. 1 times 3 is 3, so that would be a whole number. But if I multiply this last one by 3, 1.1664 times 3, I'd end up with 3.5. So that's not a whole number. That's not going to work out. 3.5, though, I can see is almost, it's an easier one to identify what to multiply it by to make it a whole number. If I multiply 3.5 by 2, I get 7. But 3 is not going to work to multiply each three of these things by. What is going to work is 6. So if I multiply 1 by 6, it equals 6. If I multiply 1.3311 by 6, I got 7.9866. Which is around 8. And if I multiply 1.1664 by 6, I get 6.9984. Which is around 7. So if the numbers are extremely close to whole numbers, like 7.9, 6.9, you can see 6.9 is going to round up with 3 significant figures to 7. We can see 7.98 is only going to round up to 7.99, but 7.99 is very close to 8. So we can confidently see that the ratio is 6 to 8 to 7. So what we have here is C6, H8, and then O7 as our empirical formula for this compound. So quite a lot of writing here, quite a lot of stuff going on. That's why I made this one, or I'll make this one the bonus question on your test coming up next Wednesday. So thanks for paying attention for this time, and let's go over perhaps one more thing. Let's go over balancing equations together in a moment.